In part 1, we followed Google's early journey into generative AI. They invented the transformer, the breakthrough that made modern AI possible, but it was OpenAI that turned it into a global phenomenon with ChatGPT. Google rushed to respond with Bard, but early inaccuracies quickly undermined user confidence, so Google pivoted. Bard was rebranded and Gemini became its new flagship model. At first, Gemini showed real promise. Larger context windows, more capable reasoning, and more realistic responses than ever before. But just as quickly as momentum built, it stalled. Bias issues surfaced, headlines exploded, and once again Google found itself on the defensive, with the internet watching every mistake. While the internet argued about screenshots, Google did what it always does in a crisis. It iterated. Hard. Gemini grew into a family, Nano for phones, Pro for most tasks, Ultra for the heaviest reasoning, and Flash for cheap, fast responses. AI overviews began appearing in search, answering complex questions directly above the traditional links.
We launched AI overviews about a year ago. It's now being used by over 1.5 billion users in over 150 countries. It's expanding the types of queries people can type in. And we see it empirically, the nature of queries is expanded. So there are whole new use cases coming into search. We find for queries where we trigger AI overviews, we see query growth, and the growth continues over time.
Under the hood, Google leaned on something few rivals could match: infrastructure. Decades of work on data centers, fiber, and custom chips called TPUs let it run huge models at scale, cheaper than almost anyone else.
For a given query, the cost to serve that query has fallen dramatically in an 18-month time frame. Google with its infrastructure, I'd wager on that, right? And on our chances to do that better than pretty much anyone else.
At the same time, Google stepped up its public argument. This wasn't just a chatbot race. It was about embedding AI into everything, from search, docs, maps, YouTube, cloud, Android, and hardware, in ways only a company of its scale can. Whether that's enough to keep developers, users, and regulators on side is still an open question. Away from the headlines about search and chatbots, Google DeepMind had been quietly rewriting the rules of science. The clearest example was AlphaFold. For 50 years, structural biologists used exotic, expensive equipment to map the 3D shape of proteins, the molecular machines that run life. They managed about 150,000 total. Then DeepMind dropped AlphaFold.
The thing that shocked me is that for 50 years, the work of tens of thousands of scientists revealed the structures of 150,000 proteins. That was the grand sum of human effort. And then in a few years, your team, small 15, 20 people, was able to find the structures of 200 million.
Instead of one PhD student spending 5 years on a single protein, AlphaFold 2 could solve one in seconds. Within a year, it had predicted structures for almost every known protein on Earth, and Google released them for free.
You see the map of the globe light up as people in real time are getting all of those structures. What was that like? Tell me, what was the feeling that you had?
I mean, look, there were so many amazing moments, and the team will remember this. But that was one of the big highlights. It was very satisfying to see that this sort of idea that if we crack this really important problem, potentially millions of researchers around the world will make use of it, and to see that sort of lighting up all across the globe is really a kind of humbling and amazing experience.
DeepMind estimates that doing this experimentally would have taken roughly 1 billion years of PhD time. And crucially, the point isn't just the database, it's what comes next.
We need to thank the structural biology community, thousands of researchers painstakingly putting together these structures using very exotic and pretty expensive and complicated equipment over 50 years, like you say, and the sum total was 150,000, but it was enough to kickstart us to be able to create a system like AlphaFold to learn from those 150,000 and then actually learn further from its own predictions and then eventually being good enough to kind of understand something about protein, something fundamental about protein structure, so then eventually we could do all 200 million.
Things have fundamentally changed, and I don't think the world gets it yet. No. And I think another thing that's really important to keep in mind is you figured out all 200 million, now they're out there, but the discoveries and the breakthroughs that are going to come from that, They're going to take decades, but we are going to be reaping the rewards of that for decades, centuries.
I think so. I mean, it's sort of opened up, and this is why we put out there into the world. We knew we could only think of a tiny fraction of what the entire scientific community might do with it. And it's really gratifying to see the whole range of things that people are already doing. Over 2.5 million researchers from pretty much every country in the world working on their really important biology and medical problems and making great progress with that. I hope we'll be able to reduce drug discovery down from taking like 10 years on average to go from understanding a target to having a drug in the clinic to, maybe a matter of months, perhaps even weeks, just like we did with the protein structures.
DeepMind spun out isomorphic labs to turn this into new medicines, aiming to design drugs that slot onto the surface of disease-related proteins like keys into locks. Beyond drugs, AlphaFold's protein structures are already being used to engineer enzymes that eat plastic, explore ideas for carbon capture, design new vaccines, and understand antibiotic resistance. Demis calls this the beginning of a new scientific renaissance, a golden age, where AI becomes a core lab tool, not just a gimmick.
AI designed drugs that were helped by things like AlphaFold and many, many other amazing things for society that will come as a downstream consequence of us knowing what these structures are now. These ideas of designing enzymes, which are types of proteins, that catalyze certain reactions and modify some of these enzymes to help deal with some environmental issues we have, like the amount of plastics in the oceans or perhaps doing even carbon capture, things like this. I think an incredible opportunity, and obviously the main reason I was interested in doing protein folding was to accelerate drug discovery.
And AlphaFold wasn't the end of the story. DeepMind's researchers began turning the same ideas loose on the algorithms underneath science itself. In 2025, they unveiled AlphaEvolve, an evolutionary coding agent powered by Gemini models that doesn't just use algorithms, it discovers them. Instead of one human expert handcrafting a clever trick, AlphaEvolve spins up thousands of code variants, tests them automatically, and keeps mutating the winners to find faster, more efficient solutions. Inside Google, AlphaEvolve has already found new scheduling heuristics that squeeze more work out of the same data center footprint, suggested tweaks to TPU chip designs, and sped up core matrix multiplication kernels used to train Gemini itself, shaving training time and energy use without changing the hardware. It's also been let loose on open maths and computer science problems, where it has rediscovered known results and in some cases pushed beyond them, hinting at a future where AI systems don't just help us apply science, they help us invent new science in the first place. Most AI today still lives behind screens. However, Google's long game is to push it into the physical world. At DeepMind's London office, football-playing robots learn to coordinate as a team, not by being told what to do, but by playing millions of matches against themselves.
Looks like fun and games, but here's the thing. Humans did not program these robots to play. They learned the game by themselves. Raya Hadsell, Vice President of Research and Robotics, showed us how engineers used motion capture technology to teach the AI program how to move like a human. But on the soccer pitch, the robots were told only that the object was to score. The self-learning program spent about 2 weeks testing different moves. It discarded those that didn't work, built on those that did, and created all-stars.
There's another goal.
Oh. I think that red player is going to grab it, but instead it just stops it. Hands it back, passes it back, and then goes for the goal.
And the AI figured out how to do that on its own.
That's right. That's right. And it takes a while. At first, all the players just run after the ball together like a gaggle of, 6-year-olds the first time they're playing ball. Over time, what we start to see is now, what's the strategy? You go after the ball, I'm coming around this way, or we should pass, or I should block while you get to the goal. So we see all of that coordination emerging.
The same kind of self-learning shows up in AlphaZero, a system that taught itself chess and Go from scratch and quickly surpassed world champions, and it doesn't stop at board games. DeepMind has been building world models, systems that learn how environments work by watching them. Models like Genie and later versions such as Genie 3 can take a single image or short clip and turn it into an interactive and controllable 3D world with basic physics. In parallel, DeepMind's SEMA project, the Scalable Instructable Multi-World Agent, trains an AI assistant across many different 3D video games and virtual worlds at once. Instead of memorizing one game, Seema learns to follow plain language instructions like go up the tower, find a vehicle, or collect the tools, even as the visuals, controls, and objectives change from game to game. Put together, these world models and multi-world agents are rehearsal spaces for the real world, places where AI can practice perception, planning, and following fuzzy human instructions before it ever touches real hardware. On the hardware side, Google and DeepMind have been publishing robotics transformer models such as RT1 and RT2, and more recently Gemini-powered robotics models that connect vision, language, and action. These systems learn from large collections of robot demonstrations and then generalize, so the same model can help different robot arms and even early humanoid robots handle new tasks they've never seen before. In the US, Waymo, Alphabet's self-driving company, has been quietly racking up millions of fully driverless kilometers, turning autonomous driving from sci-fi demo into routine transport in cities such as Phoenix, San Francisco, Los Angeles, Austin, and Atlanta. And then there's Project Astra, Google's vision for an AI assistant that can see what you see through a camera, understand context, and respond in real time.
Well, we'll have a system that really understand everything around you in very nuanced and deep ways, and kind of embedded in your everyday life.
Glasses that whisper information about the building you're looking at, robots that can follow messy human-level instructions in the real world, and cars that drive better than you do. However, each one raises the same question. At what point does an AI system stop being just software and start feeling like a new kind of actor in the world?